Hello everyone, I am Guo-Chang Wei. In the previous course, we learned about the modulation technologies at the transmit end. Today, let's learn about the demodulation technologies at the receive end. We have learned the ASK modulates the amplitude. Demodulation can be implemented directly by detecting the amplitude at the receive end. For the PSK and QAM modulations, phase is used to carry information. Therefore, coherent demodulation, the phase demodulation technology, must be used. First, let's have a look at the concept of coherence. Simply speaking, coherence is mutual interference. The concept originated from wave optics. When two waves spread in the medium and meet under certain conditions, vibration at some locations in the overlapped area will always be strengthened, while at other locations, vibration will always be weakened or even completely canceled. The areas with strengthened vibration and those with weakened vibration are mutually separated. This phenomenon is called wave interference. Waves that can interfere with each other are called coherent waves. The following conditions must be met for waves to be coherent: identical frequency, a constant phase difference, and identical vibration direction of the mass points in the overlapped areas. At the receive end, coherent demodulation uses a coherent wave of the same frequency and phase to demodulate the received signal, taking advantage of the always strengthened or weakened vibration phenomenon. As shown in the following figure, the RPSK signal is convolved with a coherent carrier at the receive end. The product of the convolution will always be strengthened when the vibration directions are the same and always be canceled when the directions are different. One of the benefits of coherent optical communication technologies is enabling the 100G and beyond 100G large capacity long-haul transmission. This is achieved thanks to the following 2 points. First, high bit rate and high information capacity to enable high-speed transmission. Second, super high polarization division multiplexing tolerance and no need for DCM dispersion compensation, enabling long-haul transmission. Now, let's have a look at the commonly used modulation technologies in different WDM systems. Non-return to zero coded ASK modulation is commonly used in 10G WDM systems. DQPSK and PDM-BPSK are commonly used in 40G WDM systems. 100G EPDM QPSK is commonly used in 100G and some 200G WDM systems. 200G EPDM 16QAM is commonly used in 200G and some 400G WDM systems. The under 200G WDM systems usually use single carriers, while the 400G ultra-high-speed WDM systems currently use dual carriers. We have to notice 2 points here: polarization division multiplexing and dual carrier. The polarization is transverse, wave-specific phenomenon. Typically, most sources of light are classified as incoherent and unpolarized, or only partially polarized, because they consist of a random mixture of waves having different spatial characteristics, frequencies, phases, and polarization states. These lights are called natural lights. All other lights are called polarized lights. Light is an electromagnetic wave, and both its electric field and magnetic field spread perpendicularly to the direction of the wave propagation. The electric field mainly interacts with materials, which is why we usually use the vibration direction of the electric field E to represent the polarization direction of the lights. Now, let's take a look at the complete process of the 100G EPDM QPSK modulation and demodulation. At the transmit end, the polarization beam splitter splits the laser light into the X and Y polarization directions that are perpendicular to each other. Then the light signals in both polarization directions are QPSK modulated. In the end, the polarization beam combiner combines the modulated signals in the X and Y directions to the same fiber for transmission. At the receive end, the received signal is split into the X and Y polarization directions first, and then the coherent detection converts the light signals in the X and Y polarization directions into electrical current, that is, voltage signals. Next, high-precision analog-digital conversion converts the voltage signals of the electrical current into digital code streams of ones and zeros. DSP compensates for interference factors, such as dispersion, noise, and nonlinear effects, and recovers the 100G signals transmitted from the transmit end. Then why do we have to use PM demodulation in the 100G high-speed WDM systems? The reason is to lower the electrical layer processing rate. With current circuit technologies, 40G BPS is already close to the limit of electronic bottlenecks. If the processing rate gets any higher, it will cause issues such as signal loss, power loss, electromagnetic radiation interference, and impedance matching. Such issues are difficult to resolve and very costly even if they are resolved. An optical signal is split into two polarized directions by PDM, and signals are modulated to the two directions. It has the same effect as to divide data into two parts, and therefore the rate is reduced by half. For QPSK, a phase equals to 2 bits, which has the same effect as dividing data into two parts, and therefore the rate is reduced by half. Therefore, a 100G signal with a rate of 112 gigabits per second is actually 28G baud when processed. Why do we use dual-carrier 400G systems instead of directly using 200G systems? To improve the system capacity. For a common 200G system, the minimum channel spacing must be 50 GHz, whereas a dual-carrier 400G system, the channel spacing of each 200G subcarrier can reach 37.5 GHz currently. This greatly improves frequency usage and can transmit larger capacities within the same band. However, the largest capacity and the longest transmission distance cannot be achieved at the same time. The capacity and transmission distance of an optical transmission system is always the outcome of a dynamically balanced selection. As shown in the figure, when the system capacity gets larger, the transmission distance without regeneration becomes shorter correspondingly. After these two courses, do you guys have a clear understanding of coherent communications, 100G and 400G WDM systems? Let's have a brief review. The following characteristics of light waves can be used in communications: amplitude, frequency, phase, and polarization. WDM systems use these characteristics with technologies such as ASK, FDM, PSK, QAM, and PDM. ASK can be directly detected and demodulated. PSK and QAM require coherent detection and demodulation because phase modulations are involved. PDM enables us to make more use of light waves and transmit signals using different polarization directions. That's all. Thank you for listening.